This week we're going to be talking about volume. Today in particular, we're going to be looking at the volume of prisms and cylinders. What I thought would be a good way to introduce the concept of volume would be to have you draw actual examples of what these units are. So volume units are going to be what we call cubic units, which are literally little cubes. And what we do when we calculate the volume is we account for the number of cubes that it would take to completely fill an object. Okay, so what I thought would be neat here is if you actually drew a cubic centimeter. What we do is we start like what we had done in area where we draw a square that would be 1 centimeter by 1 centimeter, but then we give it a little bit of depth. When I drew the pictures, I actually drew it as about half of a centimeter. That way it didn't seem to look too like stretched out, so I did that. But this is a centimeter, that's a centimeter, and you have a square, and then you also have the depth that should be a centimeter. Of course, I drew it as half of a centimeter. I did the same thing for an inch over here, so I did the square inch, but for the depth, I did about half of an inch there. And I think that gives you a fairly good idea of like what that looks like, and if you were to like attempt to pick it up. So this is a cubic inch, and this is a cubic centimeter. So when we say something has like a volume of 50 cubic centimeters, that means it would take 50 of these cubes to create that. For this next part, what I want you to do is create a rectangular prism that has a volume of 36 cubic centimeters. In other words, you're going to be creating a box that can contain exactly 36 of these cubes. To do this, I'm sort of relying on the assumption that you know how to calculate the volume of a rectangular prism. If you don't, then you can kind of just skip ahead and look at what I do. But I think what would be really worth it here is for you to give this a shot first and see what you come up with. The neat thing about the 36 is, man, there is a lot of different combinations and or designs, I should say it that way. There's a lot of different designs of a rectangular prism that can have that volume, and I think it's kind of a fun activity to let you attempt to come up with what you can. Here's the picture that I ended up drawing. I went with like a base length of 6, a base width of 2, and then a height of 3. And my front face, you could also describe that as having a length of 6 by 3. So depending on perspective and how you want to describe it. But I ended up using these numbers. I guess we'll talk about the calculation as we go through this part here, but 6 times 2 times 3 does give you 36. To do the problem, I am relying on the assumption that you remember how to calculate the volume of a rectangular prism, which is length times width times height, and we're going to develop that here. So there's a bunch of different ideas that you could have come up with. The one that I always think is kind of fun when people think of it is the 1 times 1 times 36. If you just had like 36 cubes all like in one row. But you can come up with all kinds of things. You could do I don't know, put 2 dots there. You can do 9 times 4 times 1. You do that. You could do 9 times 2 times 2. So there's a lot of different combinations how you can build it. And as long as the different dimensions that you have multiplied to give you 36, then you did it right. Okay, so going through this part here, then, well, we'll see how that turns out. All right, so the way that we can think of the volume of a prism is to think of it sort of as a building. So I'm going with an analogy here. You can calculate the number of cubes, and remember, this is all about cubes. How many cubes can we like fit inside of the thing? You can calculate the number of cubes on one of the levels, okay, on one of the levels, so like a base level of these, the number of cubes by multiplying the length times the width. Okay, so now this is perspective that I'm letting this be the length, that'd be the width, and then this is going to be the height. Okay, so you multiply the length by the width. Okay, and then once you have that product, so if you look at my picture, and this might be a little bit confusing with all the little pink lines in there, but if I multiply 6 by 2, I'm getting 12. And what that means is I have a total number of 12 cubes that are sitting in the bottom. So if I want the complete volume of this thing, then what I'm going to do is multiply that 12 by the number of rows I would have. So then I multiply this product, that's the 12, by the number of levels, which would be 3. Whoops. Number of levels. I'm going to call that height. Started using the actual numbers here, and I want to use the words. And that becomes your volume. So I would have 12 times 3 different rows or height, levels of these things, and I end up with 36. So ultimately, the volume formula that you're probably used to here is length times width times height. Here. So the last example was strictly for, when we did length times width times height, that was strictly for a rectangular prism. So if you look at a figure like this, you can't multiply the length times the width times the height. One of the things that I always talked about with area, and I kept running this idea, was that if you are going to multiply any of the measurements in a figure, they have to be perpendicular. So if you were to go to this image and start trying to multiply numbers like the 10 times the 8, that's okay because that's at a right angle. But what else are you going to multiply it by? If you do 10 times 8, you can't multiply by this 8 because that angle is not going to be a right angle. Okay, so we need a better way of describing how to calculate these volumes. All right, I might as well just read from the top here. The volume formula for a rectangular prism works for all prisms and cylinders. Just replace the product length times width, the L times W, with what it represents, which is the base area. Okay, so for every prism and cylinder, there is a way that you can set it up almost like a loaf of bread, and you can slice through it so that you get this unique cross section along the figure. So in this case, that cross section is going to be that triangle. In a cylinder, that cross section is going to be a circle. And those unique shapes are what we call the base, and each of those shapes is going to have an area. Okay, so our formula for the rectangular prism was volume equals length times width. But what we're going to describe it as is the volume is base times height. That is a capital B that we're going to be using because that B represents a calculation of finding that cross-sectional area, and then the H is like the length of the figure and the number of like rows or levels or slices that you would have of that. Okay, so let's take a look at the triangular prism that we have here. Okay, so we're going to use base times height, but base is, being that capital letter, base means that it represents more stuff. So our cross section for our base, our cross section for that capital B is the triangle that we see here. So our volume, we begin with the concept of base times height, but that base is always going to be changing out to something special from problem to problem. In this case, it's going to be 1/2. I'm going to write little b times, and this is where it gets confusing here, because there's a base and a height that refer to the triangle. But then there's another height, which is like the length of the figure, and that one here is the 10. So I'm going to go ahead and get that one filled in. It's this length here. I'm going to get that one filled in, and now the rest of this is going to be focused on the cross section. So a lot of the time what I'll do is I'll just draw that cross section over to the side. Okay, now take a second to think, what is special about that triangle? And you should have thought it is an equilateral triangle. That we have 8 by 8 by 8. So this is going to be that special case that we've seen before where when you draw that height, it's going to break the figure into a 30, 60, 90 triangle. And there's a couple of them there. Okay, so when it breaks, let me go ahead and just draw one side of it so it's cleaner here. That hypotenuse is 8. This is going to be a 4. And this height, so here, this is your 30, 60, 90. I don't know if I want to write that, but I'll try. That height, I hope you know your shortcuts, is going to be 4 square root 3. So if you remember those shortcuts, you'll save yourself a lot of time doing the problems. So now, values from here are just going to transition into this. The base is going to be that length there, which is 8. The height is the perpendicular to that, which is the 4 root 3. Then you had your 10, and when all of that is multiplied together, you will have yourself the volume. What I'm going to do here is just keep it in radical form. I'm going to leave the 3 in there. So The 1/2, I can multiply that by the 8. That's going to give you a 4. And then I got 4 times 4 is 16. 16 times 10 is 160. So we can just write this as 160 root 3. And our units, which I'm always bad at writing, so if I remember them, I'll try and get them in there. That's going to be inches cubed. You can multiply this if you want to get a better idea of what it is. The square root of 3 is it's approximately 1.73. Okay, so you can imagine multiplying that by this number and then whatever you get from there, but I'll leave the answer in that form. Last example for this set of notes is going to be this goofy looking shape here, which is called an oblique cylinder. Oblique basically means that the figure is sort of like being pulled to the side. I don't want to quite say that it's leaning over, but it's being pulled in a certain way. The bases are still going to be parallel to each other. Okay, so here's the deal. If you have an oblique cylinder or just an oblique prism, so imagine a rectangular prism doing sort of the same thing here, the volume doesn't really change, and your method of how you're going to calculate it doesn't become anything different. You're still going to have that capital B, which is whatever your cross-sectional shape is, and you're going to multiply by like its true height. Be careful, and this is where the problems are a bit tricky. Don't use what would be like a slant height to it. Remember, everything has always got to be perpendicular. Do not multiply things that are not perpendicular to each other. Okay, so I'm going to attempt to record this and see if it makes sense when I do it, but I have a whole bunch of washers here that, of course, when you stack them, they look like a cylinder. And from that view, all you really see is the circle part, so I'm going to have to pick it up here. Okay, so you have a cylinder, and it has some volume to it, whatever the calculation this would be. If I were to start like shifting the washers, and it's a little bit hard to, if I were to start shifting them so that it looks like that, the volume doesn't change. The volume doesn't change. Your cross section is still going to be the circle, and you still have the same number of washers, which would be like the height of it. See if I can hold it better here on the paper. Okay. I really want to make this look right, but it's hard. Okay, it's probably about the best I'll do. Okay, you do get like these little steps in it, but I wouldn't pay too much attention to that, because if we were to use something that was a lot thinner, like maybe a stack of paper, those little ridges in there wouldn't really be noticeable. Okay, so the idea here though is that when you create an oblique figure, like all these little slices are just slightly moving out to the side, and it does not change the volume that we have on there. Okay, so if my visual there wasn't too great, here's the gist of it. It doesn't matter if it looks like this or if it's standing upright. You are still going to calculate using that formula. You're still going to figure out the area of a cross section. In this case, it's a circle. So you're going to do a pi r squared. And you're going to multiply that by the length, like the perpendicular length of this figure, so by the height. Okay, so the volume of this is going to be pi. Our radius is 4. Always watch out that it's not a diameter, but this one's being nice to you. So you're going to get 4 squared. I just naturally squared it because I can't stop myself from doing that sometimes. And then your height is going to be a 7. Just don't use any slant heights because, like I said, they're not perpendicular. All right, you could leave that in terms of pi if you want, or you can multiply it all together. I should be able to multiply that fine. That's going to be 70 plus 42, which is 112 pi. I hope it is. All right, our units here are going to be centimeters cubed.